Hello everyone, welcome to the channel of Algocamp. So now on this particular channel, we are actually releasing a series on data structures and algorithms where we are going to talk about some of the most important data structures and algorithmic topics which are extremely important for your upcoming software engineering interviews. Apart from that, these are some of the I would say topics that are very helpful in your day-to-day engineering job as well. We have already released a couple of series around searching, right? And we got a really good response on that. And from here, we are going to put really some awesome content around DSA. In most of these lectures, we will try to ensure that we focus on the intuition building aspect of the things, that how you are able to think about something, what are some of the things that people actually neglect but are going to clear some of the really important fundamentals. We are going to see coding implementation, but trust me, my focus is not going to be on the language delivery aspect of the things, that okay, you have to code this in C++ or Java. A lot of problems we have coded in multiple languages. Maybe some of the problems will be in C++, some will be only in JavaScript. I believe if you are somebody who is preparing for an interview, language in 2025 should not be a constraint, because most of the people can actually use ChatGPT to do language conversions. So my motive here is to make sure that you understand the concept in depth. You actually see how exactly somebody might have thought about the problem when they were carving out the problem, what can be some initial thought process, how you can actually drive yourself towards the solution. I believe these are going to be some really important videos that will be really helpful for your upcoming career. So do let us know what is your feedback. We are going to release a lot of more topics. Do let us know what all topics you want to have first, right? And the feedback is going to be important. Also, in case you are actually thinking to level up, you want to learn things with respect to low-level design, high-level design, overall system design for interviews, or you are somebody who wants to do project development in Spring Boot, you want to learn advanced Spring Boot concepts, or let's say advanced Node.js concepts, then we have a lot of courses, live courses running on algocamp.io. So you can check out the website courses.algocamp.io/learn, and there are a lot of courses that are actually listed. A lot of great discounts are actually going on all the courses as well. Do check them out. For each and every single course, we are going to add you to a dedicated Discord community where you can get your doubts resolved as well. All of the courses, we have made sure that we talk about things from the very beginner to the very advanced level that is going to help you level up in your career as a software engineer. So that being said, let's start the video without any further delay. Now let's say if I ask you, what is the time complexity of MergeSort? Now MergeSort is kind of like a complex implementation, and its time complexity also cannot be just directly calculated, right? We cannot just say that, okay, total number of recursive calls multiplied by time taken in one recursive call, because total number of recursive calls are like quite strange and we won't be able to just directly get it, right? So in order to solve the time complexity problem of divide and conquer solutions, we have a different kind of recursive relation, right? We have a very special type of recursive relation. So for example, you consider quick sort, binary search, merge sort, any of these algorithms, which are divide and conquer algorithms, they are going to follow a very special type of recursive relation. The recursive relation looks something like this. Let me first of all write it, and then we will talk about it. So T of n is equals to A into T of n by B plus f of n. This is generally the recursive relation that a divide and conquer solution possess. Now you might be thinking, what is A, what is B, all of this. Let me come back to it and actually write in front of you what will be the recursive relation for MergeSort. So let's say if I write a function T of n, that calculates number of operations required to do merge sort on an array of length n. So before we start this particular video, I wanted to actually talk about a very small thing. So this video is going to actually help you understand a real system design interview scenario. We are going to try to mimic a 45 to 60 minute kind of like a round where we are going to solve a problem very similar to how you will solve a similar system design problem in this short time frame. Now, of course, when you work as a software engineer in a company, you have relatively larger amount of time and you can do a lot of more deep dives in even very small level features. But in an interview, the temperament is different, the approach is different, and a similar scenario is actually explained in this particular video. So do consume the content based on that. Also, if you want to see more deep dives and want to understand these topics in a much more deeper level concepts, then do check out the link in the description section below for our System Design 2.0 cohort, where we have talked about a lot more concepts in a lot more detail, which will make you definitely a better software engineer. So let's just start the video. Right. Let's say T of n represents the number of operations you are going to require in order to apply merge sort on an array of length n. Now you tell me, when you have an n length array, you divide it into two arrays of n by 2 length and n by 2 length, and then apply merge sort on these two arrays. You apply merge sort on the left half, merge sort on the right half. So can I say the number of operations are going to be equal to, this is going to be equal to number of operations you require to sort the left half plus number of operations you require to sort the right half. So see, left half is n by 2 length, right half is n by 2 length. If T of n represents the number of operations to do merge sort on n length array, then T of n by 2 will represents the number of operations to do merge sort on an array of length n by 2. Same thing here. So this is the number of operations to sort the left half. Number of operations to sort the left half and number of operations to sort the right half. And then once the left half is sorted, and once the right half is sorted, once both of the halves are sorted, then what do? You actually merge both the halves. So if you remember, merging two sorted arrays where one sorted array is of length n and another sorted array is of length m, the time complexity is order of n plus m. So here we have an array of length n by 2, another array of length n by 2. So what will be the time complexity to merge two arrays of length n by 2? Can I say n by 2 plus n by 2, which is what? O of n. So can I say, in order to do merge sort on an n length array, if you want to calculate number of operations to do merge sort on an n length array, it will be equal to number of operations to do merge sort on left half plus number of operations to do merge sort on right half plus big O of n, right? Plus big O of n, which if you simplify becomes something like T of n is equals to 2t n by 2 plus O of n. See, 2t n by 2. If you see this divide and conquer relation, here a is equals to 2 and b is equals to also 2. And then you have a function of n. So if you see, this is the upper bound of the function f of n, that is O of n. And can you see, this looks like a divide and conquer relation only. And if you will write the relation for quick sort, binary search, or any kind of a divide and conquer relation, it is going to be coming up something like in this form, right? And this form is very interesting because you can't just directly solve this form. Like now you have this form. What is the value of T of n? If I talk to you that in terms of big O notation, what will be the value of T of n? You won't be able to just directly calculate it. You need to make some extra effort, right? And this question was like asked to me in my interview of Bloomberg London, that I was asked to derive the time complexity of merge sort followed by the derivation of time complexity of any divide and conquer algorithm, right? So this observation is going to be very important. And now we are going to solve this recurrence relation. I'll show you that how you can solve this recurrence relation in a very easy manner, right? Which will help us to solve this kind of a generic divide and conquer relation. And we will be able to come up with some formulas that we can apply in order to solve these kind of, I would say, divide and conquer relations. So now we are going to see that after each recursive level, what is the size of the problem that it becomes, how many number of problems we have at each level, and how many operations we do at each level. Okay. So initially, can I say the length of my array is n, right? The length of my array is n. So the size of the subproblem is n, right? If f function sorts an array of size n using merge sort, then this is f of n. So initially on the, let's say, 0th level, you have n size problem and there is only one such problem. Can I say that? Then you divide your problem into two parts of size n by 2 and n by 2. Can I say that? So size of the problem becomes n by 2. And how many such problems of size n by 2 are there? There are two problems of size n by 2 on level number 1. Then on level number 2, size of the subproblem will become n by 4. And there will be 4 such problems of size n by 4. Can I say that? See, n by 2 and n by 2 will give you n by 4, n by 4. Here also it will give you n by 4 and n by 4. So there are 4 problems of size n by 4. So I'm just writing the size of the problem is now n by 4. And there are 4 such problems of size n by 4. If you move ahead on level number 3, the size of the subproblem will become n by 8. And there will be 8 such problems of size n by 8. So on and so forth. On some ith level, the size of the subproblem will become n by 2 raised to the power I. And there will be total 2 raised to the power I subproblems. You can see it here. On level 0, the size of the subproblem is n by 2 raised to the power 0. And number of subproblems is also 2 raised to the power 0. On level 1, size of the subproblem is n by 2 raised to the power 1. And number of subproblems is also 2 raised to the power 1. On level 2, size of the subproblem is 2 raised to the power 2. And number of subproblems is also 2 raised to the power 2. On level 3, size of the subproblem is also n by 2 raised to the power 3. And number of problems is also 2 raised to the power 3. So on any ith level, the size of the subproblem will become n by 2 raised to the power I. And number of subproblems will become 2 raised to the power I. Can I say that? And so on. And so on. On the last level, let's say kth level, on some kth level, can I say my problem size actually becomes 1, because on the base case, that is the last level, the size of the subproblem actually becomes 1. That's the base case, right? Can I say that? So what will be the number of subproblems in that case? Can I say the number of subproblems will be somewhere around 2 raised to the power k? If k is the last level. Now what is the value of k? Let's see what is the value of k. What is the value of k? So at the last level, the size of the subproblem should be n by 2 raised to the power k. See, on the ith level, size of the subproblem is n by 2 raised per I. So on kth level, it should be n by 2 raised to the power k. And we know the value of n by 2 raised to the power k, it is equals to 1, because on the last level, size is 1. So n is equals to 2 raised to the power k. Taking log both sides, it becomes log of n base 2, we are taking base 2 log, equals to log of 2 raised to the power k base 2. Log of n base 2 is equals to k log 2 base 2. K will come in the multiplication. And what is log 2 base 2? Log 2 base 2 is 1. So k becomes log of n base 2. Can I say that? Right? That means at the last level, the number of subproblems is going to be what? 2 raised to the power log of n to the base 2. What is 2 raised to the power log of n to the base 2? Can I say n? And this is obvious, right? Because merge sort actually starts dividing your array into 2 parts, into 2 parts, into 2 parts. At last, you have all the elements in one length arrays. So how many total elements are there? N elements. So at the last level, there are n subproblems, and we have also derived it very easily. And the value of k is going to be what? Log of n to the base 2. Okay, cool. Now let's see how many operations you have to do on each level, because our time complexity will be sum of all of these operations, right? That's what the recurrence also says, that number of operations to sort the left half plus number of operations to sort the right half plus O of n. So that's what it takes, right? Okay, let's see. how many operations you require in order to merge two sorted arrays of n by 2 size to make it n? Can I say we need n operations? Can I say we need n operations? Okay. So this can be equal to 2 into n by 2. Okay, cool. Now, this is n operations on 0th level. Now, on first level, in order to calculate how many operations you require on the first level, how many operations you require? Number of operations is going to be the number of operations to sort the left half and the right half, that is n by 4, n by 4, and n by 4, n by 4, plus number of operations to merge these halves. Now just think about it. If you merge two sorted arrays of size n by 4, it will take n by 2 unit of time. Here also you have two sorted arrays of size n by 4, it will take n by 2 unit of time. So total time is what? N by 2 plus n by 2, that is n. So can I say if you have 4 arrays of size n by 4 and you are going to actually merge all of them, you are going to again take n unit of time. Let's see. You have two arrays of size n by 4, n by 4. If you have to merge them, this will make n by 2. Then you have another two arrays of size n by 4 and n by 4. In order to merge them, you take total n by 2 unit of time. So what is the total unit of time taken? N by 2 plus n by 2. This is the total time, which is equals to n. And we can also say this is like 4 into n by 4. Same thing here. There will be 8 arrays of size n by 8 and n by 8 and n by 8 and so on. You will merge them to make 4 arrays of size n by 8, n by 4. Total time taken will be what? N units again, n units again, n units again, so on and so forth. At last level also n units. Can I say that? So what is the time complexity? Time complexity is going to be total number of operations. Time complexity is total number of operations, right? Because if you see T of n is a time complexity. It is equals to what? Number of operations you require to sort your left half and right half. What is the number of operations to sort the left half and right half? These many operations are required. Then only your left and right half become sorted. Plus O of n. Plus O of n. So if I just sum all of them up, I'll get number of operations to actually do merge sort on n length array. So you can see n plus n plus n plus n, so on and so forth, n. How many times? Log n times. So you have T of n is what? N plus n plus n, so on and so forth. N how many times? Log of n to the base 2 times. So the total time complexity will become what? N log n. And in big O notation also it is going to be order of n log n. Right? And n log n is far, far better than order of n square. Right? So this is how you can derive the time complexity of merge sort. That is, you try to see that how many operations you are doing in each level and in each sub problem, and then based on that you try to form some observations. Now let's just talk about the space complexity. Okay, discussion on space complexity is going to be really very interesting, to be very honest. So if we carefully see merge sort, right, if we carefully merge sort, then there are two type of spaces getting used. If you see the coding implementation of merge sort here, then we are using recursion. That means recursive call stack space is definitely getting used, because recursion is nothing without the call stack, right? Can I say that? So call stack, right? And the second space is, the other space is in order to create these auxiliary arrays. These two auxiliary arrays that we are creating, this is also the extra space. So auxiliary arrays. Okay. To merge. Okay, cool. Now, how much space call stack is taking? What do you guys think? How much space call stack is taking? Now, you know, when merge sort is going to work, it is not going to work parallelly. because these recursive algorithms are not parallel algorithms, right? So how MergeSort will grow? This is one function call. It will make a function call here. It will make a function call here. It will make a function call here. This is the base case. This function call will get removed and you will make a this function call. This is again a base case. You will go back and then you're going to resolve this and then you're going to go back. So you are left with this and then you go here, then you go here. So can you see at any point of time, only one particular branch is going to get saved inside a call stack. When you make a call stack, this function call, then this function call, then this function call, and then this function call. Because this is a base case, this will get removed. Then you make another function call here. Then this will also get removed and you have left with 3. Then this will be resolved. You are left with 2. Then you make another one. You are 3, then 4. Then you are again left with 3, then again 4. Then this is also done. This is also done. So now you are left with these 2. Then you make a call here, 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 and so on and so forth, right? So at any point of time in the call stack, in the worst case, only one single branch will be present. So, and one branch is, you know, how many calls you are going to take in one branch? Log n calls. So this is going to be order of log n. At least the call stack space is order of log n. That is what we know. And you can even visualize here, one call here, one call here, one call here. So how long is the branch? The total number of levels is equal to the number total length of the branch, and total number of levels are order of log n. Okay. This is the space of the call stack that is going to get used in the space complexity. There is one more space, auxiliary arrays, but I hope this call stack space is clear to everyone. So now let's talk about the auxiliary space of these arrays that we are going to take. So there is a very interesting article on Stack Overflow, right? I'll link this article. So inside this article, they have very well explained how space complexity you can try to imagine, right? If you see the question, what was asked, they are discussing about the merge sorts time in space complexity. So how, so this question you guys can read, but let's see how they are actually seeing the overall complexity in terms of space. Okay. So you can say it's written here, merge sorts time complexity is n log n, which is a fundamental knowledge. We have already derived it also, like technically. Merge sort space complexity will always be order of n, including with arrays. Now, as I said, there are two parts. One is this call stack and auxiliary array. So total space is what? This space plus this space. So log n plus whatever is the space auxiliary arrays are taking, that's what the space complexity. And this article claims that it will be always order of n. Let's see how. If you draw the space tree out, space tree is something like this, just like how we have recursive tree for like operations. It's the space tree for how much space we are going to take. It will seem the space is n log n. If you see this tree, it will look like it's n log n, but it's not n log n. Let's see how. However, as the code is a depth first code, because we are writing it recursively, and these kind of recursive codes are depth first, like you explore one branch completely, then only you go to the next branch. Like at any point of time, you are processing one branch, one complete depth. So as the code is a depth first code, you will always only be expanding along one branch of the tree. And this was always I was talking about. You always go in one branch for the processing. Therefore, the total space usage required will be always around bounded by order of 3n, which is order of n. For example, let's say you have an initial array of size 16. Okay. You will divide them 8, 8, 4, 4, 2, 2, and so on and so forth. But you know, right, that this is not going to be parallel. So technically what will happen? From 16, you will go to the left half, that is 8. Right half will wait. Then you go to the left half, 4. Its right half will wait. Then you go to the left half, 2. Then 1 and then 1. What is the total space? 16 plus 8, 24. And 24 plus 4 is again 28, 29, 30, 31, 32. This is what? 32 units of space for this branch. And 32 is what? Less than 3n. N was 16. 16 3 is a 48. So 32 is less than 48 definitely. Now, if we are done with this call, we are going to expand in the other branch. Now, this 4 will get its right half sorted, right? So left half is now sorted. This 2 length is sorted. Now we are going to sort this half. For sorting this half, we will need this. So 16 plus 8 is again 24, plus 4 is 28, 29, 30, 31, 32, 33, 34. 34 is also less than 3n. Now, if these two are sorted, you will merge it here. And now you will make a call to the right half of 8. If you make a call to the right half of 8, this is going to get now sorted because left half is already sorted. This is 16 plus 8, 24, 4, 28, 4, 32, 34, 35, 36. 36 is also less than 48. And so on and so forth. Like you can always capture this. You can always capture this. It will be always less than 3n, whatever space, like at any point, because once one branch is completed, that space is going to get removed, right? You have garbage collectors, or if you have language like C, C++, you can manually delete it. So whatever auxiliary arrays that we are using here, once the function is done, this array A and B will be getting removed in the garbage collector. So this at any point of time, whatever branch we are processing, only that much space we will be using. And you can see that space is always bounded by 3n. So order of 3n is what? Order of n. So this is a very interesting article. You can read more about this in this article, but they have like very simply explained everything. And if you want to intuitively see also, you can see in one function call, in the worst case, you will be creating an array of size n, right? And then in the next call, it will be n by 2. Then in the next call, it will be n by 4. So you can see n by 2, n by 4, n by 8. So this is going to be somewhere around order of n only. It will not go to n log n, right? So the space complexity is order of n. So I always use this article to explain things around space because it gives you a kind of like an experimental analysis kind of a thing, which is exactly true, right? So that's the space complexity of MergeSort.